Right, everybody. I am on page, 78 here to talk about area and volume. So find your way to your packet. We won't need a calculator yet, but you might need one in a minute when we get to our second key lever. So the first thing I want to talk about is area between two curves. We've got a good, sorry, I don't know why that's doing that. We've got a good model problem here that we can use to highlight the idea behind this key lever. What's the area of the region enclosed by these two graphs? Y equals x minus 4x squared and y equals negative 7x. Without a calculator, the best thing for you to do is to draw this. Negative 7x is a pretty steep line with a decreasing slope that goes directly through the origin. And then y equals x minus 4x squared. That's kind of hard. I know that's a quadratic function, but I'm going to take an x out to see if maybe I'm a little more successful with what this looks like. X times 1 minus 4x. So I have one root at 0 and another root at like 1/4 if I set each of those pieces and factors equal to 0. So this is a pretty skinny Sorry, y'all, someone walked in my classroom. This is a pretty skinny parabola that I'm going to have to draw. And again, if you're not sure what I'm talking about, I'm setting the factored form equal to 0, which gets my first root at x equals 0 and my second root at x equals 1/4. So I'm going to switch colors and try and draw that skinny parabola in here. And I'm going to make sure that my parabola is opening down because of the negative sign that's on that quadratic term. So I'm going to try to draw something. Oh no, I don't know if I can undo just that. There we go. Okay, I'm going to try again. I'm going to go through the origin and then over at 1/4, a pretty narrow parabola. Forgive my bad picture, you know I'm the worst. And really what I want to try and make sure I capture here is that I'm going to try and find the area here bounded by those two graphs. So the biggest idea and the biggest key lever for this is that area is equal to the integral from sum a to b of our top minus bottom with respect to x. And this is going to be a pretty standard run through of an area computation. So if I just stand over here in my region and I look up, the function on top is definitely going to be that x minus 4x squared quadratic. And then I want to subtract the function down below, which is the negative 7x. I'm going to add that 7x and actually do a little combination of like terms here so that I have a simpler integral. And I'm dealing with the integral of negative 4x squared plus 8x, which I can integrate. That's not a big deal, but I don't know my bounds yet, so that's something that's going to be a little bit tricky. I do notice on my picture that one bound is, over here at 0, 0. That's where they both intersect on the left. And then the other bound is down here where my curves intersect further down in quadrant 4. If I had a calculator, it would be really easy to just set the calculator up to do the intersection for me. I don't have a calculator, so I need to kind of slow down and understand that the calculator sets the two equations equal to each other when it finds those intersections. So I'll move the 7x to the other side. This is 8x minus 4x squared equals to 0 when I do some computation. That looks familiar. That's what I had over there when I combined my like terms. I can solve this by factoring out a 4, which leaves me with 2 minus x equals 0. And this confirms that my first intersection is at 0, and it looks like the second intersection is going to be at 2. That's really helpful because now I can do the problem. So let me integrate. A negative 4x squared had to have come from a negative 4/3 x cubed, and that 8x had to have come from 4x squared when I do my antiderivatives. So thankfully, I'm really only going to have to worry about the upper bound because the lower bound is going to result in a 0. So that's negative 4/3 of 2 cubed plus 4 times 2 squared. I'll do some math. That's negative 32/3 plus 16. Specifically, that's 16 over 1. So again, some mental math. That's negative 32/3 plus 48/3 when I get a common denominator. And it would appear as though my answer is 16. thirds, and I'm done. All right, and the next key lever is volumes of solids with known cross sections. Just before we go into this, that was when I had squares or semicircles, isosceles triangles, equilateral triangles, rectangles. All of those are possibilities. What we're doing here is taking our region that's 2 dimensions and putting solids of those shapes like stacked on the region right next to each other. So here we have a piece of candy that's determined by the curves plus or minus x cubed between 1 and 2, as shown in our figure. For the candy, the cross sections perpendicular to the x-axis are equilateral triangles. What's the volume of one piece of candy? So just to make sure I'm clarifying, that top curve is actually the x cubed function, and the bottom curve, oh dear, hold on. The bottom curve is the negative x cubed function. So it's important that we distinguish that there are 2 curves here. And then I also want to make sure you understand that we're slicing this and using equilateral triangles here to kind of build this piece of candy. So something that we reviewed back in Unit 7 is that the area of an equilateral triangle can be found using the formula root 3 over 4 side squareds. That's how I can find the area of one equilateral triangle. To get the volume of this whole solid that has an infinite number of those equilateral triangles, we integrate. Thankfully, they've given us bounds 1 to 2. And I have that root 3 over 4, it's nice to take that out, times the side squared. I'm choosing to put a dx on my integral because we're perpendicular to the x-axis. And if I can just uncover what the quantity of that side is, then I can integrate and be done with this thing. So that side, look over here, the side is just the distance of that rectangle, the length of the rectangle from top to bottom. So we ask ourselves what's on top, x cubed, minus what's on bottom, negative x cubed. I have to do a little bit of math here. So the first thing I'll do is add those x cubes, and I see that then my integral becomes root 3 over 4 integrals from 1 to 2 of 2x cubed squared. I'll actually square that, and my integral becomes, let's see, from 1 to 2, 4x to the 6th, because that square means 2x cubed times 2x cubed. And now I can do some integration. I have that root 3 over 4, and now a 4/7 x to the 7 from 1 to 2, which the 2 goes in first, root 3 over 4 times 4/7, I'll clean that up in a minute, times 2 to the 7 minus root 3 over 4 times 4/7 of 1 to the 7th. Sorry, y'all, Mr. Abdul is like yelling next door, so I'm trying to tune him out. These 4's cancel. And I've got, let's see, 2 to the 7. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64, times 2 is 128. Promise I get 128 root 3's over 7 minus 1 root 3 over 7 for a final answer of 127 root 3's divided by 7. Okay, now finally we're going to talk about volumes of revolution. So our next key lever involves the graphs of e to the negative x and the sine of x, and the region that's bounded between those two things in the y-axis in quadrant 1. First thing we want to do is find the volume, and we spin around the x-axis. So I've gone ahead and opened up my calculator and graphed those two equations, and kind of changed my window a little bit. So I want you to grab your calculator and do the same thing for me so that we're all looking at the same thing. So pause the video if you need to. And here's my window in case you're curious. Since I was only needing what was in quadrant 1, I adjusted to a pretty small viewing window so that I wasn't overwhelmed with the rest of the graph. So I would do the same thing if I were you. But now to visualize what's going on, I'm going to take one slice of this, and sorry about that, and try and spin it around the x-axis. So let me go ahead and just snip this image so that you can see what we see, and I can draw all over this thing. All right, so here we go. Here's my graph, and what I want to do is take this region between my two blue and red equations in the y-axis and spin this thing over, there's my representative rectangle, over the x-axis. So that means it's going to land down here, and I'm going to generate a nice washer for myself. So the first thing that I'm thinking now is that this is going to be a volume problem with a pi times some integral of my outer radius squared minus my inner radius squared with respect to x, because I was spinning around that x-axis. So if I can uncover what the outer radius is and what the inner radius is, I'll be able to go to my calculator and finish this thing up. So let's think about radii for a second. A radius of the outer circle, here's my outermost circle, is the distance from its outermost edge to its center. So what I'm trying to do is uncover the length of that blue shaded line right there. So I ask myself, what's on top of that? Well, that's the e to the negative x function. And what's on bottom? Well, that's 0. So e to the negative x minus 0 gets me an outer radius of e to the negative x. Do the same thing on the inner circle. Here's my inner circle. It's small. And the radius there is the length of that black shaded bar. So what's on top of the black bar is sine x. And what's on the bottom is 0. So here we go. My inner radius is just sine of x minus 0. I'm pretty confident just looking at this picture that the lower bound on my integral is 0. I'm unclear right now what the upper bound is. I feel like it's going to be that intersection over here, so I'll call that a and then go back to my calculator to figure out what that quantity is. So let me toggle back over here, and I'm going to go to menu 6 number 4 and just compute that intersection real quick. There it is, 0.61163. I'm going to click it and control store as A so that I have access to that from here on out. And I'm going to just toggle over and get my integral taken care of. That's pi times the integral from 0 to a of my outer radius squared, which, shoot, I always forget. Let's go make sure I don't mess this up. It looks like my F1 is, oh no, you guys, my function's a mess. Let me try again. Were you wondering if your values were not the same as mine? Okay, sorry, somehow some junk got stored up there in my F1 function, but I fixed it. Now look, that did adjust my intersection. So if you were thinking I was crazy earlier, you're not wrong. The intersection is actually 0.588. It updated automatically because I stored that. So thankfully I don't have to go redo my intersection. Let me just make sure I didn't screw up the other function too. So, okay, I got sine of x in correctly. I had just messed up the first one. Okay, my outer radius and inner radius they're not changing though. So F1, that first function, e to the negative x, is my outer radius that I want to square, minus the inner radius is the F2 function, that sine curve. And with respect to x, my answer is 0.887. Okay, and the last thing they asked me to do here is take this same region and this time spin around the line y equals 2. So that's the line way up here. I'm going to take this region and spin it around that line. So this disk, this washer that I had kind of translates way up here. So what's interesting is that the setup is the same. I'm going to have pi times the integral of some outer radius squared minus some inner radius squared with respect to x, but my outer circle has definitely changed. Now, it's this huge circle on the outside, and the radius of that circle is the distance from the edge to the center. So it's a bigger radius, and I ask myself, what's on top of that red line is 2. Minus what's on bottom of that red line is the sine function. I can do the same thing for the inner circle. Here it is. Inner circle has a radius indicated by the blue bar. What's on top of that is still